Hello, and welcome to our final project presentation. My name is Nolan McCulloch, and my teammate is Kate Stowiger. And for our final project, we did a quality analysis on finish crack investigation performed at Kate's work. So, kind of describe a little bit of the nonconformance. What happened is, in a process of metal plating a brass faucet, a crack started occurring on the finish, and this was non-desirable and caused the product, each sample that this occurred on, to be scrapped. And so an investigation was opened to identify the root cause of this issue. The data that was collected to identify this problem was were these items here. The first was a sample number, so each sample would be given a unique identifier. Second, a finish color, whether the plating was intended for a rose gold finish or maybe a silver or other available SKU. Third, there was a nickel plating measurement that was taking place in 4 different locations on each faucet. And this was also true for the chrome plating, which was again taken in 4 different locations to measure the chrome plated thickness. And then lastly, we have a crack status, whether there was a crack observed or not observed a crack, and which plant the faucet came from. So to kind of get an idea of the process variation, we did an ANOVA analysis, and how we split the ANOVA up was by taking the chrome plated measurements and the nickel plated measurements and separating them up, because there was quite a bit of variation different in the mean and variation of the chrome measurements versus the nickel. So within each set of chrome and nickel measurements, we also separated out the plant 1 versus plant 2 so that we could see the variation between plant 1 and plant 2 for the chrome measurements and plant 1, plant 2 for the nickel measurements. Both plants were using the same recipe as far as concentration and formulation for the metal deposition. And so to try and tease out any variation in the process, this ANOVA was done to kind of hone in to and identify variation in chrome and nickel plating on a plant-to-plant level. And you can see here, as we look at the ANOVA table for the chrome-plated measurements, that our p-value is incredibly low. So we have a high confidence that there is a difference between plant 1 and plant 2 in the results that they're finding in their metal deposition. And something else to note is we have an e to the negative 80, and I mean that's pretty low. But as we go to our nickel, we can see that p-value drops even more. So there's even more unexplained variation in the process for nickel than there is for chrome. And Kate will talk a little bit more to that in the other analysis that we did. But from our ANOVA, we have indication that there is variation difference plant to plant that can't be explained by normal variation, and also there's slight variation we could look into between nickel and chrome. So I'll hand it over to Kate to continue our presentation and come up with some of the improvements and recommendations. On to you, Kate.
Hi, thanks, Nolan. So next on the analysis that we did with the data was looking at the nickel thickness and the chrome thickness and charting that out on a control chart. So although it's not in a sequence, we can still see how many of these spouts had thicknesses above and below the control limits. So up in the upper corner, you can see the range for nickel thicknesses as well as the range for chrome thicknesses. And this is analyzed down on the bottom charts for the nickel and the chrome. What we see on, firstly, the nickel, that's the first layer that goes on, is the first 30 plus points are at that upper limit or above. And then beyond that is on the lower limit. So really no balance in that middle. Unfortunately, because we can't do it sequentially, what we see is that the first section are from plant 1 and the second section are from plant 2. So although these are all plated at the same plant, we did notice there is a difference between when they were plated, what kind of thicknesses the nickel was giving. And then secondly, we look at the control chart for the chrome. And again, all of those at the upper limit, not really pointing out any patterns because again, it's not sequential, but we can see that they're all at that upper limit. As it comes to field testing and what will work well in the field and give the best results, we do see higher nickel thicknesses do give better results for salt spray testing, for all the G85 testing that has to happen there. And so having on that lower thickness level for the nickel on all of those parts that were tested at our second plant, although plated at our first plant, that can throw off some of those concerns for the longevity and the field controls. So then the next step that we did was take a look at the correlation analysis. So what we have are the 3 different factors, which is the average nickel, so the 4 points of nickel thickness taken on that spout averaged out, the 4 points of chrome taken on every spout averaged out, and whether it was plated or whether it was PVD'd at plant 1 or at plant 2. So the plant, the average nickel, and the chrome are the 3 factors that were tested against each other for this correlation analysis. The first thing of note is the result versus plant. And so what that is saying is at what plant it was PVD'd at and whether it had the crack showing or not. So we do have a 0.877 correlation, positive correlation for the plant. And so what that's saying is there is a high correlation between what plant it was PVD'd at and whether we could predict the crack or not. Another high point to notice is the nickel thickness, and the plant had a very had a correlation there. So, and we could see that in the control chart as well. There was a high correlation between what plant it was at and the nickel thickness, and that was just when that was plated. So we don't really have a great understanding because they were all plated in the same plating line on the same plating racks. So more to come on that analysis there, more data to be dug into. But really focusing on that first column then is we do have that 0.75 negative correlation between the results, so whether it was cracking or not, and the nickel thicknesses, and a negative correlation of 0.57 for the chrome. So the highest correlation that we have to predicting whether it was going to crack or not is what plant it was PVD'd at. The next step is the nickel, and really not a huge correlation between the chrome. So that nickel thickness does play a factor, but the highest factor that plays into it is the plant. And so will we see cracking at the plant? What we dug into with that information is there's something different in the process of PVDing based on this correlation analysis. So something is different at the plant level for PVD at that plant for the PVD at that plant level. And so what is different in those recipes? So the recipe is just that cloud of chemicals. So whether it be carbon or nitrogen, and that puts that color on the faucets after chrome. So is it going to be gold, rose gold, nickel? It gives you all of that color variation. So both of the plants have the exact same chambers, so the exact same equipment, as well as the exact same recipes. Those are created by the Advanced Development Group. When they create the colors, they create those standards and hold those standards. So when we look at those recipes at each plant, there was significant difference between plant 1 and plant 2 that was noted after we saw this correlation analysis. And that is the cool down process. So it was verified that at plant 2, the recipe had been changed. These parts have to be heated up to over 400 degrees Fahrenheit when they're going through this vacuum chamber, and then they have to be cooled down at a rated cool down rate, so that way they come back down to room temperature. The problem was at plant 2, we could see that the recipe had changed, and that cool down process happened too quickly. They sped up that cool down process in a lot of conversations after that to speed up the process and get more parts through, thinking it didn't make a big difference. Unfortunately, having that change in process and cooling it down too quickly can affect that chrome and that nickel layer and that PVD layer and create that crack. So it is very possible and probable, based on the analysis done, that that cool down is what really, that speeding up of the cool down process is what's causing that crack at plant 2 primarily. And so something to move forward and do that verification of that, we don't, just because we didn't have the time frame here to put all the parts through the whole process and do it, taking it as homework to verify that and to run a set of parts through with a quickened cool down procedure and the normal rate for cool down and compare those two at the same plant is critical. Just don't have time within the time frame of this class, but we can say that there was that indeed factor. So to control that process is really locking out the system. So we haven't done this in the past, but it is capable of doing it, is locking those systems out, locking up the temperatures, locking up the recipe controls, the timing temperature, the timing of when they're heated up and cooled down is critical. So locking that out for our advanced development team who creates these recipes to to make sure that nobody's messing with them and changing those times. So that's happening throughout the week. And then understanding that nickel variation is also critical because there was that 0.75 correlation between the results we were getting, whether it was cracking or not, and the nickel. And we could see on the control charts as well that there was a very low nickel thickness on some of those parts. And so understanding what is changing in that plating process that causes that change in nickel. Some of it can be what parts are running at the same time. There's a lot of factors that need to be controlled and understood. And so having a periodic test with the chemical engineers to understand some of the thicknesses of the chrome and nickel on those spouts and start that control process is that next step. But again, the highest correlation that we saw was for the plant, and so controlling that PVD recipe is critical moving forward. All right, we did use the book as a reference, and so we have that here. So thank you all for listening to our project on chrome-plated faucet defects.